Hello, my name is Corentin Kervadec. I'm happy to present to you some of our recent works focusing on biases and reasoning in visual question answering. These works address the issue of reasoning versus shortcut learning. Shortcuts are defined as decision rules that perform well on standard benchmarks but fail to transfer to more challenging testing conditions. VQA models are notorious for their tendency to rely on shortcuts. In this illustration, the model fails to predict that a star is on the wall because this is an infrequent event. The predicted answer, painting, suggests that the model prefers to provide a frequent answer. I will now introduce some of our work which evaluates, analyze, and improve VQA models. In the first paper, accepted at CVPR 21, we propose a new benchmark for evaluating shortcuts in VQA predictions. Our benchmark, called GQA out of distribution, is based on the observation that concepts are naturally imbalanced in VQA corpuses. It is constructed by rearranging evaluation splits of the already existing GQA dataset. First, we split the dataset into fine-grained question groups. In the example, this is the group addressing object on the wall. For each group, we construct the answer histogram based on the frequency. Some answers are very frequent, and others are rare, such as a star. We see that a majority of the state-of-the-art models fails to provide the correct but rare answer. Based on these observations, we identify the head and the tail of the distribution and propose three metrics: accuracy all, accuracy tail, and accuracy head. Evaluating state-of-the-art models with our new metrics, we observe a huge gap between tail and head accuracies. This demonstrates the strong dependency on shortcuts. In particular, if we look at the tail accuracy as a function of rarity in this graph, we measure that accuracy dramatically decreases on the rarest examples. Surprisingly and paradoxically, we observe the same results with bias reduction methods specifically designed for VQA. We complement this study with a publicly available demonstration, exploring the question of reasoning versus bias exploitation in VQA. This interactive tool visualizes attention heads of vision language transformers. It is instant-based and provides a fine-grained visualization of the interactions at work in the attention layers. This instant-based analysis of attention mechanisms at work in transformer VQA models brought us to a more systematic study. This is the subject of our second paper accepted at CVPR 21, where we conduct a deep analysis of several aspects of VQA models linked to reasoning. In particular, we claim that shortcut learning in VQA is in part caused by the uncertainty in the vision part. Therefore, we propose an experimental study with vision language transformers, where we compare the attention mechanisms at work in two settings. The first one is the standard VQA model, where the images are represented as a set of objects extracted using an object detector. But this representation is imperfect. Objects can be missing, falsely detected, or even detected multiple times, which favor shortcut learning during the training. For this reason, we propose the second setting, called Oracle, where the model is trained with ground truth input objects. In the paper, we analyze and compare learned attention mechanisms in both settings, including attention diversity, attention pruning, and links between attention and reasoning functions. We show significant differences between Oracle and standard models. More importantly, the Oracle model shows a strong relationship between attention and task function, which we interpret as the capability of adapting reasoning to the task at hand. In contrast, the standard model seems to lack these abilities. Drawing conclusions from our analysis, we propose to transfer learned reasoning patterns from the Oracle to the standard model through pretending and fine-tuning on initialized weights. This simple transfer allows us to boost accuracy on the GQA and VQA2 datasets. Our transfer also increases accuracy on our GQA OOD benchmark, which I have previously introduced. Finally, our latest work proposed to extend the study of the Oracle transfer in order to improve it. For this purpose, we supervise the VQA model to predict the sequence of reasoning operations required to answer the question during the transfer. In addition, we provide a theoretical analysis based on pack learning, demonstrating that such supervision can lead to decreased sample complexity. We implement the method by adding a program decoder on top of the vision language transformer. As shown in the table, the supervised transfer in blue allows to improve the performance of the Oracle transfer previously introduced in red. In addition, it achieves an accuracy comparable to the state-of-the-art, while using a smaller model and much less training data. As a conclusion, we have addressed several aspects of the visual question answering task linked to reasoning. We have evaluated the bias dependencies, analyzed the reasoning patterns, and improved the model's performance in both in and out distribution settings.